Hello students, in previous lecture we had discussed about the basic definition of power series, classification of singularities and some examples. In this lecture we will discuss about the series solution about an ordinary point. Okay. This method is also called as power series method. So let us discuss first steps how to find a power series solution or series solution about an ordinary point. Okay, for that let us consider the differential equation p0x, the second derivative of y with respect to x, plus p1x, first derivative of y with respect to x, plus p2x into y is equal to 0. We say this as equation number 1. Now we follow these steps. So in this method, at the beginning, we are assuming our solution. So in step 1, let us assume that y is equal to summation n running from 0 to infinity a suffix n x minus x0 raised to n be the solution of equation number 1. Here a0, a1, a2, a3 are the coefficients that we need to determine, that we need to find. Why this only? Because x is our variable, x0 is known, it is our ordinary point. So the remaining are only the coefficients. So our remaining method is to find these coefficients. Let us go for step 2. Here we do differentiation of this y with respect to x twice. Means we find value of y dash and y double dash. Then we substitute the value, or we can say expression of y, y dash and y double dash in the given differential equation 1. Then in next step we will shift summation index so that each term is of same power. See, once we get the power of x is same in each and every term, also the summation index is same, then we equate to 0 the coefficient of various powers of x and find a2, a3, a4 and so on in terms of a0 and a1. Once we get values of all these coefficients, we substitute that values in the equation number 1. That will be our required solution. Let us consider example. Find the series solution of d square y by dx square plus x square y is equal to 0. The answer is, now here we want to find series solution. Actually we want to find power series solution about an ordinary point. That's why we try to find first ordinary points of this differential equation. So here we are given d square y by dx square plus x square y is equal to 0. We say that as equation number 1. Now observe that p0x, the coefficient of d square y by dx square is 1. there is no term containing dy by dx. So p1x we write as 0 and coefficient of y, that is p2x, is given x square. So p of x will become 0 and q of x is x square. So note that here all the points of R are ordinary points. Why? Because in the denominator of p of x and q of x there is no term containing x. So there will be no singular point. Okay? So all points are ordinary points. Okay. So let us take x0 is equal to 0 because 0 is also an ordinary point. So we find series solution of equation number 1 about x0 is equal to 0. Okay. So let us solve step by step. So in first step we assume that y is equal to summation n running from 0 to infinity a n x raised to n be our solution, okay, where we need to find a0, a1, a2 and so on. Okay. Next we differentiate y twice with respect to x, okay, to get y dash and y double dash. Okay. So let us differentiate first y with respect to x. Here the variable is only x raised to n. Right? So if we differentiate this with respect to x, then the derivative of x raised to n will n x raised to n minus 1. So our dy by dx will summation n from 0 to infinity n a n x raised to n minus 1. Now in this expression, if we put n equal to 0, then our first term will be 0. So we can write this summation as summation n running from 1 to infinity n a n x raised to n minus 1. Okay. Because of derivative, summation index is not changed. Summation index changed from n equal to 0 to 1 because if we put n equal to 0, then first term is 0. Right? Similarly, the second derivative, that means the derivative of x raised to n minus 1. So it is n minus 1 x raised to n minus 2. So our d square y by dx square is summation n running from 0 to infinity n minus 1 a suffix n x raised to n minus 2. Here again, if we put n equal to 0, the first term will be 0. If we put n equal to 1, the second term will be 0. So that we can also write this summation as summation n running from 2 to infinity n minus 1 a n x raised to n minus 1. Okay. Now we have values of y dash and y double dash. So we put these values in equation number 1. Okay. So we can write summation n running from 2 to infinity n minus 1 a suffix n x raised to n minus 2 plus x square, then expression of y, that is summation n running from 0 to infinity a n x raised to n is equal to 0. So first term is as it is, but in second term outside summation we have x raised to 2. So we take x square inside the summation. So the second term becomes summation n from 0 to infinity a n x raised to n plus 2. Okay. Okay. Now in next step we try to obtain power of x same in each terms. Here in first term power of x is n minus 2. In the second term, power of x is n plus 2. There are two methods. Either make power of x n minus 2 in both the terms, or make power of x n plus 2 in both the terms, or we make power of x is n only in both the terms. For our conveniency, we make power of x is n in each term. Okay. So in first term put dummy m, that means we want here power of x is n, right? So we put n minus 2 is equal to m. Right? So we can write n is equal to m plus 2. Once we have taken n minus 2 is equal to m, in the whole term, whenever we see n, instead of n we put m plus 2. So our first term will summation m plus 2 running from 2 to infinity, m plus 2 minus 1, a suffix m plus 2 x raised to m. Same way, in the second term, power of x is n plus 2, but we want to make power of x is n. Instead of n, we are taking m. So for second term, assume that n plus 2 is equal to m, right? That implies n is equal to m minus 2. So in second term, whenever we see or wherever we see n, instead of n put m minus 2. So our second term is summation m minus 2 is equal to 0 to infinity a suffix m minus 2 x raised to m is equal to 0. Hope you understand this step. Now our m was dummy. We need n. So we put m is equal to n in both the terms. Meanwhile, we are taking this in first term, the 2 right hand side, right? And in second term, minus 2 right hand side. So see the first term, if we take 2 in the right hand side, our summation starting from m is equal to 0 to infinity. But instead of m, we are putting n. So our next step is summation n running from 0 to infinity n plus 2 n plus 1 a suffix n plus 2 x raised to n, plus the second term is summation n running from 2 to infinity a n minus 2 x raised to n is equal to 0. Now power of x is same in both the terms. So next step is make summation index same. That means both summation should start from same number. The first summation is start from 0. In the second summation, second term, summation start from 2, right? So if we put n equal to 0 and n equal to 1 in first term, then this summation will start from 2. Okay? So let us put n equal to 0 and 1 in first term. If we put n equal to 0, we will get 2a2. If we put n equal to 1, we will get 2 into 3, a3x. Then remaining terms are plus summation n running from 2 to infinity n plus 1 n plus 2 a suffix n plus 2 x raised to n, and the last term. Now we can see last two terms. See, in both we have summation index and both starting from same number. Okay. So we can take summation index common and x raised to n common from the last two terms. So we can write 2a2 plus 6a3x plus summation n running from 2 to infinity, then in bracket n plus 1 n plus 2 a n plus 2 plus a n minus 2 bracket over outside x raised to n is equal to 0. Then next step is we equate 0 to coefficients of various powers of x. Here first term is coefficient of x raised to 0, second term coefficient of x raised to 1, and the last term coefficient of x raised to n. So 2a2 is equal to 0, that implies a2 equal to 0, 6a3 equal to 0, that implies a3 equal to 0, and the last term n plus 1 n plus 2 a suffix n plus 2 plus a suffix n minus 2 is equal to 0. Here suffix of first term, that is n plus 2, is bigger, that's why we make recurrence relation about this a suffix n plus 2. So write a n plus 2 is equal to, take a suffix n minus 2 in the right hand side, so it will minus a suffix n minus 2 divided by n plus 1 into n plus 2. This recurrence relation is valid for all n greater than or equal to 2. How can we write this? See, the previous one, we have recurrence relation from this term, right? And this term here, for that summation is running from 2 to infinity. That means it is valid for n equal to 2 to infinity. That's why we write this recurrence relation is for all n greater than or equal to 2. Now we put different values of n starting from 2. If we put n equal to 2, we get a4 is equal to minus a0 divided by 3 into 4. N equal to 3, then we get a5, it will minus a1 divided by 4 into 5. Then for n equal to 4, we get a6, it is minus a2 divided by 5 into 6. But we have a2 is equal to 0. So a6 will become 0. Similarly, a7 is 0 as a3 is 0. Then we find a8, a9, both will depend on a0 and a1, and so on. Now we substitute all these values of the coefficients in equation number 2. Our assumption of solution. So our assumption of solution was what? Y of x equal to a0 plus a1x plus a2x square plus a3x square plus and so on. So a0 as it is, a1 as it is, because we don't have value of that 2. Then a2 is 0, so this term will become 0. a3 is 0, so this term will become 0. Then the fourth term is a4 x raised to 4. We are getting a4 minus a0 upon 3 into 4, so we put that minus a0 upon 3 into 4 into x raised to 4. Then fifth term a5 x raised to 5. a5 is minus a1 upon 4 into 5 into x raised to 5. Okay. Then a6 x raised to 6 and a7 x raised to 7 both are 0. Then we write 8th term plus and so on. So in some terms we have a0, in other terms we have a1. So we take common. So first we take a0 common. So in bracket we have 1 minus x raised to 4 upon 3 into 4 plus x raised to 8 upon 3 into 4 into 7 into 8 minus and so on, plus a1. Also we have x common in remaining terms, so we can take x outside. So plus a1x in bracket 1 minus x raised to 4 upon 4 into 5 plus and so on. This is our required solution. Hope you can understand this example 1. Let us consider example 2. Here the question is, find the power series solution of y dash minus 2xy is equal to 0 in powers of x. Okay. The question can also written as, find series solution of y dash minus 2xy is equal to 0 about x equal to 0. From first statement, we can say that we need to find the solution in powers of x. That means a0 plus a1x plus a2x square plus and so on, like this. And in the second statement, we are given that find series solution about x equal to 0, right? That is, we need to check whether x equal to 0 is ordinary point. Okay. If it is ordinary point, then we can find a series solution using power series method. If it is not ordinary point, we need to check whether it is regular singular. If it regular singular, we have to solve this example using the Frobenius method that we will discuss in the next lecture. Right now, let us consider the given differential equation y dash minus 2xy is equal to 0. Here keep in mind, there is no term containing the second derivative of y. Right? We have only the first derivative and the term y, term containing y. So here we will not write p0x. So coefficient of y dash is p of x, that is 1, and coefficient of y is q of x, that is minus 2x. Okay. Here since p of x and q of x both are polynomials, so they are everywhere differentiable. Therefore we can say that they are everywhere analytics. So all points of set of R are ordinary points. We need to concentrate on the point x equal to 0. Here x equal to 0 is also an ordinary point. So let us find the series solution of given differential equation about x equal to 0. Okay. So in first step, we assume our solution. So let us assume y is equal to summation n running from 0 to infinity a n x raised to n be our solution. Then we differentiate y with respect to x because we need y dash. So y dash is summation n running from 1 to infinity n a n x raised to n minus 1. We put expression of y and y dash in equation 1. So we get summation n from 1 to infinity n a n x raised to n minus 1 minus 2x summation n running from 0 to infinity a n x raised to n is equal to 0. Now we take x inside the summation. So the second term will become summation n running from 0 to infinity a n x raised to n plus 1 is equal to 0. Okay. Now next step is make equal power of x in both the terms. In first term, power of x is n minus 1. In second term, power of x is n plus 2. We make power n in both the terms. Now here I am not taking dummy m. I directly put, see here in first term, you can understand, instead of n, if we put n plus 1, then plus 1 and minus 1 will cancel out. So power of x will be n. So if we put n is equal to n plus 1 in the first term, whole term, wherever we are getting or we are finding x, in the whole term, whenever we have n, instead of n we put n plus 1. Okay? So The summation index is n plus 1 is equal to 1 to infinity. If we take 1 in right hand side, then summation will start from 0. Then instead of n plus 1. So n plus 1, a suffix n plus 1 x raised to n. See here, we get this. Similarly, the power of x in second term is n plus 1. We want power n only. So instead of n, we put n minus 1. So in the second term, wherever we have n, instead of n, we put n minus 1. Right? So the summation is n minus 1 to infinity. If we take 1 right hand side, then summation will start from 1. Right? So it will be summation n running from 1 to infinity, a suffix n minus 1 x raised to n. Okay. If you don't understand this, you can take dummy m and then put m is equal to n. Now power of x is same in both the terms. Let us make summation index same. Here first summation is start from 0 and the second summation start from 1. So in first summation or in first term, we put n equal to 0, so that the remaining terms will be start from 1. Okay. So put n equal to 0, we get 1 into a suffix 1 x raised to 0. That means it is a1. So a1 plus summation n running from 1 to infinity. We take this summation index common and x raised to n common. So remaining is n plus 1 a suffix n plus 1 minus 2 a suffix n minus 1. Next step is equating 0 to the coefficients of various powers of x. So first coefficient of x raised to 0, that is a1. So a1 is equal to 0. Then n plus 1 a suffix n plus 1 minus 2 a n minus 1 is equal to 0. Okay. We make recurrence relation about a suffix n plus 1. So a suffix n plus 1 is equal to 2 a n minus 1 divided by n plus 1. Again, this recurrence relation is valid for all n greater than or equal to 1 because of this summation index. Now we put different values of n. Put n equal to 1. We get a2 is a0. N equal to 2. We get a3 is in terms of a1. But a1 is 0. So a3 will be 0. If we put n equal to 3, we get a4, that is 2a2 by 4. It is a2 by 2. But a2 is equal to a0. So a4 is equal to a0 by 2. Then if we put n equal to 4, a5 will depends on a3. But a3 is 0. So a5 is 0. So continuing in this way, we get values of all these coefficients in terms of a0. Now we substitute these values in equation 2, our assumption of solution. It was y is equal to a0 plus a1x plus a2x square plus and so on. So we are getting a0 plus 0 into x plus a0x square plus 0 into x cube plus a0 by 2 x raised to 4 plus and so on. Here a0 is common in each and every term. So we take a0 common. So y of x is equal to a0 in bracket 1 plus x square plus x raised to 4 by 2 plus and so on. This is our required series solution. I hope you all can understand these two examples as well as the method of power series. Okay. If you solve these three examples, you will clear about this power series method.